PhD student here at Michigan State in computational biology, and he has also written what some people call the seminal book on Python and machine learning. And so he's been jet setting around the country to different conferences, giving talks on machine learning and specifically the scikit-learn package. So yeah, and he's also ranked really highly on, I think #1 maybe, on the Analytics Vidya list of data scientists to follow on GitHub. So we have someone really special in our midst here. Without further ado, I'll give it to Sebastian.
Yeah, hi everyone, and thanks for coming, and thank you for the nice introduction. Really appreciate it. And yeah, for the topic, usually I give talks on machine learning and things like that, but today I thought, because I think a lot of people are new to data science, I maybe should give a little introduction about not only what data science is, but how to get into data science, and basically how I got started like a few years ago. And yeah, Adi last week had a nice kind of little summary of data science. Like a data scientist is a person who's better at statistics than any software engineer and better at software engineering than any statistician. And maybe a shorter one would be a data scientist is a data analyst who lives in California. And you will see in a moment where I'm getting with this. And because there are many definitions of a data scientist, so it's not really like fixed term, and it just came up very recently, but it's a very important popular term nowadays. So how many of you know this Venn diagram? It's yeah, oh, only one. It's coming up in every talk, and I thought it's a classic. I should put it in here at least. And so what this Venn diagram by Drew Conway basically symbolizes or says is data science involves many different skills from different subfields, such as like programming, the hacking skills, math and statistics, and domain knowledge. And if it all comes together, you know a little bit of programming, you can write your programs, your data analysis pipelines, you have a little bit of statistics knowledge, and you know a little bit about the domain, for example, biology or finance, then you may want to call yourself a data science because it's very sexy on your CV nowadays. So yeah, and I think data science, the term, has been around for 50 years. There are some old literature where it came up already. But I think where it really became popular was when Jeff Hammerbacher, he's at Cloudera, when he tried to define his job, his current position, what he's doing. And I found this nice one here on Quora. So what he basically says is, I told the story at my presentation at Bauer. So, and I decided that we needed to combine the term data analyst and research scientist into one single one. And this is probably how the term data scientist became really popular. So as you can see, it's basically a data analyst who also yeah, is more applied doing research, but also has some coding skills. And a little bit nicer, what I think is a really nice overview of the skills that or the tasks that a data scientist usually does is from this nice book here, Doing Data Science, from Cathy O'Neill and Rachel Schutt. And they basically, it's just an example, they made a data science or data scientist profile. And I'm not sure if everyone can see this here at the bottom. So these are basically the different skills or things that you want to do when you are working on data science problems. For example, you maybe want to have some skills, or it's very important to have data visualization skills, because when you're analyzing your data, there are numbers, but you also want to visualize it to not only explore your data, to understand your data, but also to communicate it to your maybe collaborators, to your boss, to your management division. And communication skills, data visualization are important, but then also to get the data, to analyze the data, you need to know a little bit of statistics, and machine learning is very popular nowadays, basically predictive modeling. And for that, to better understand machine learning, you also want to have some math skills. For example, calculus to understand how optimization algorithms work. And then you have also the computer science aspect. What's also very important, I think, for in my projects, for example, that I have a rough understanding how computers work, operating systems work. For example, when you know how your limitations of your memory, how you want to store your data efficiently, like databases like SQL, HDF5, and things like that. And also you want to kind of be efficient with computing clusters. We have this supercomputer here at MSU, and knowing how to use it goes a long way. I mean, it's very powerful, and I think accounts are free, so sooner or later, if you're not already using it, you probably want to sign up for an account as a HPCC cluster to also use the computing power that we have here at MSU. And so there's one part, and you don't have to be an expert at all of them. I mean, this is why this is not a uniform distribution here. So everyone has maybe a kind of a little bit of different strengths. So, I mean, you can't be a jack of all trades. You should know a little bit about everything, I think, but you can't, I mean, the day only has 24 hours, right? You can't be an expert in all of these areas. And usually, in practice, you work in teams, usually. In academia, it's a little bit different. Teams are smaller, you have a few co-workers. But I think in companies, you really have a subdivision where people are really spending time on writing optimized code. There are people who are coming up with ideas, and people who are managing your storage or server stuff. So you don't have to be an expert in all of them, but it's good to know a little bit about all of these. And this is basically summarized in another graphic from this book, that when it comes all together, you have a team with people that have different strengths, and in combination you basically work on these problems together. And usually I give talks about machine learning. And this one is a little bit more about data science, but I'm just wondering how many of you have heard of machine learning? Oh, all of you. Then it's kind of boring because I thought, okay, no, if I would have asked this maybe 3 years ago, I would have maybe gotten 3 hands, I don't know. It's a very popular term these days, and so I thought giving a short introduction, like 3 slides on machine learning, we can skip that if it's too trivial, but maybe why not? So machine learning is basically the automation of predictive modeling. In a nutshell, how it usually works is you have a set of inputs and outputs. This is a special case of machine learning, a classification example. And you feed it to an algorithm, and what comes out is basically a hypothesis or a program that you can use to do certain things. Maybe the simplest example is a spam classifier. So what you can do is the trivial way, the old way is basically you, as a human, look at all these different emails, and maybe you see, okay, if this email contains the word Viagra, okay, that is probably a spam email. And then you go through all these emails, and oh, this is like an advertisement, this is probably spam. And then you label them all by hand, and then you find rules, and it takes a lot of time, and you have to read all these emails. And your rules are probably also not that good. And nowadays what you can do is basically, or this has been around for a long time, you can use machine learning algorithms, and what you do here in this email example is you have a set of emails, you have a set of labels, so you know whether it's spam or not spam. You use your algorithm to optimize or find a hypothesis, a predictive rule that can do this automatically. That's basically machine learning in a nutshell. And there are many different applications of machine learning nowadays in our everyday life. I mean, almost everything is powered by machine learning nowadays. So our spam filter in the very left that I touched on briefly, I mean, it's just a subset of images because it's hard to find images without violating any copyrights, so these are free images. Yeah, and I think a good old example is ATM. I think it was in the 80s, the first deep neural networks, convolutional neural networks by Jan LeCun, where he trained, or his system was, I think, one of the first ones that was used in ATMs. What they did is basically image recognition on the numbers to automatically read in the checks. Makes a lot of things easier. And yeah, of course, recommendation engines. I just put Netflix in here, but it could be Amazon and anything else that you are, or we are all using. Basically ranking results, finding search results based on our behavior. And then this cute little Google car, I think it looks different now, it's just one image that I found. Like, that's where we are going with this. This is reinforcement learning, like building or using AI basically to have robots, automated cars, chess computers, and even Go computers now, like the board game Go. And yeah, there are 3 categories of machine learning: the supervised learning, unsupervised learning, and reinforcement learning. Spam classification would be one example of this kind of supervised learning where we have the labels. But sometimes we're also working with data sets that don't have any labels. For example, in biology, it's pretty big. If you use or work with genomic data, you don't have any labels. You want to do some exploration or even compress the data. And reinforcement learning, the car, for example, or a chess computer, is basically a multi-step process where you have a system and not a direct response, but a kind of a delayed response. For example, in a chess computer, you want to give the computer a reward for every move it makes, but ultimately what counts is, does the computer win the chess game or not? It's basically like reinforced by playing chess and then learning whether it won or not or lost. And just very briefly about supervised learning, it's maybe one of the biggest fields in machine learning in terms of research, but reinforcement learning is also pretty big nowadays. It's the new trend maybe this year. In supervised learning, we also can categorize it in two subcategories, like regression and classification. And now you're wondering why regression, why do we call this machine learning? Because we can also use statistics. So in machine learning, when we do regression, we usually use some optimization algorithm, like an incremental learning algorithm. And in statistics, I mean, there's a closed form solution, for example, for linear regression, for this special case. There it involves a matrix inversion, and this can be expensive at some points. Like the computer is maybe not capable of inverting a matrix that has millions of rows because you have memory limitations. Here you can, for example, also use machine learning to learn this function or hypothesis incrementally. And the difference between regression and classification is basically in regression you have a continuous output. Could be a number, for example, if you want to predict a credit score would be a number, for example. And in classification, like this email example, you have labels or names like spam or not spam, but you can also have multiple classes. But what's important here is in classification you don't have any order in the labels. You can just say or think of them as names. Colors would be, for example, one example. But the point here is really you don't have any order. You want to find categories. For example, in image classification also. And briefly also about clustering or unsupervised learning. So unsupervised learning can also be broken down into two categories. You have clustering and basically dimensionality reduction or compression. And in clustering, you want to find groups of similar items. Here I just have a very simple data set, a 2D data set, and I want to find groups that are similar to each other based on some similarity or distance metric. And in compression, you basically usually want to, there are two also different types of this, but usually you are concerned with overfitting. For example, you want to remove noise of your data set, but also it can be helpful to visualize your data. If you have a high dimensional data set, this is a very simple example. I can analyze or plot a 2D data set here in a scatter plot, but if I have millions of features, I can't really visualize this. And with compression or linear, with dimensionality reduction algorithms, I can also compress this onto a smaller dimensional subspace. I think in this case, I used a kernel PCA to reduce this two-dimensional subspace onto a one-dimensional one. And as you can see, this is also called manifold learning. What I do basically is I compress it in a way that maintains the spatial relationship between these dots. So think of it that the blue ones are belonging together and the red ones are belonging together. And then if I apply this algorithm, I can basically squash it into one dimension. And here I could use a linear classifier just to draw a boundary and classify this more easily, for example. It's just one example. And yeah, that was basically machine learning in a nutshell. The title of the talk was Getting Started with Data Science, so I will continue with that. But any questions so far? No? Because everyone already knew machine learning, sorry about that. I really didn't know, it's okay. So about getting started with data science, I suggested this topic because I also got started with it not too long ago, a few years ago. And what worked basically for me is these three things here. Reading about stuff, taking classes, but honestly, I think the most important part is then also doing these kind of things and really implementing things and then also communicating with others, getting feedback and also letting the community help you to find errors or misunderstandings and clarifying things. And yeah, I think, I'm not sure, is anyone taking any data science, machine learning related class? Which ones are you taking? maybe starting here.
So one of them is computational data science engineering.
Ah.
There's a course in that.
And what are you taking over there?
Introduction to Machine Learning.
Ah, is it, which number is it? Which course number?
It's 491.
Oh, that's new. Okay, cool. No, because when I came here, there was only 901 course or something. They have a new professor now, Professor Zhu. I talked to him once.
Yeah.
He made the new lectures. Pretty nice professor. So, but I think it was more like an advanced class if you already had some background. I didn't take this class because at this point it was a little bit too redundant, maybe. But I took pattern classification. I think it was CSE 801, 802. It was a great class. We had Aaron Ross, who was a new professor, and it was probably one of the best professors I ever had. We didn't have any presentation slides. It was just chalkboard, and he really went through the equations, proofs, and derivations. It was a statistical pattern classification, and I really learned a lot there. And another great one that I took was Professor Tan. It was data mining 830 maybe, I don't know. And this was a little bit broader about data mining techniques, but also heavily focused on machine learning. I mean, these are two courses I maybe would personally recommend. Helped me a lot. And there also I have a section on books that I read that I found really helpful. But taking classes and reading are only two parts of it. And I think what really helps is doing things and thinking creatively, solving problems, because ultimately algorithms and programming languages, they are just tools to get your job done, right? It's more about getting insights about data, answering questions. And I have this here in a step-by-step thing. So one thing how I, for example, when I did things is, I read about a new concept. For example, there was a new algorithm that I haven't heard before. Let's say it's kernel PCA. And I read about this, I found different literature on this, and okay, made sense to me, but do I really understand this? So I took my favorite programming language, Python, and it could also be R. I was pretty much into R like until 3 or 4 years ago, and then more about that later. But so I implemented it. I mean, there are already implementations out there in open source software packages, but what really helps is without looking at them, implementing it yourself, and then seeing or checking, do you get the same results that you get when you run the open source package where it's already implemented. And I had some bugs in there, and it helped me really to really understand translating the math from the paper into code and actually using it. It's something you wouldn't probably use in the real world because they are more efficient implementations, but I think it's really great for learning. And then I also wrote a lot of blog posts back then, or shared stuff, because it helped me really to get feedback. First, I think it has two advantages. The first advantage is really you get feedback in terms of, did you get it right? Did you understand it? The second is you will get a lot of nice emails about people who found this helpful, which is really nice if you hear, oh, you could help someone out with this. And then also, the last thing is maybe you can put it on your CV if you write a short paper about this or put a project out there. So I think there are only benefits from also sharing your work if this work is not, if you're allowed to share this work, I think it's great. Everyone benefits from this. I mean, most of the tools we're using nowadays are open source tools that people are developing in their free time. And it's really huge if a lot of people are working on these tools, working together on these